starting point of our graph. This graph is represented by A, some maximum value, times cosine because it's an oscillation, times omega times time because it repeats over some time scale, and it depends on the time t. So if we look at this graph and we ask about cosine and the starting point, we might ask, what is x at t equals 0? So that's a good question. X of 0 equals a times cosine of omega times 0 equals a times the cosine of 0. Cosine of 0 is just 1, equals a, and that matches our graph. So let's ask what that means. That means we've put a mass on a spring, we've set it oscillating, and we turned on our stopwatch, or we hit collect on the computer to start recording our data when x was equal to the amplitude. So that's what this graph is representing, is that our first point was taken when x was equal to the amplitude. But let's ask, does that have to be true? Does our first point have to be taken when x is equal to the amplitude? What if we started our stopwatch right here? Or what if we hit collect when our x was right here? Would we still have the same motion? And the answer to that question would of course be yes. If we started our stopwatch right here, here's x of 0. It's not at the amplitude, but it's still some point on the oscillation. It still goes up and down. It still oscillates over some time period, the same time period, and it still depends on t, and it still has the same maximum value. The only difference is we hit start when it was right here instead of right here. So how do we deal with that? So when we look at this graph, x of 0 is not equal to the amplitude. So now we're asking, what do we do about that? So let's ask, x of t still has some of the same things as above, still has the same maximum value, so we still need our amplitude in there. Still goes up and down as a sinusoid, so we still got to call it cosine. It still oscillates over the same time scale, so it has the same angular frequency omega, still depends on time, but it doesn't have the same start. It has a different value of x when t is equal to 0. So we need something inside that argument for the cosine, and the something we need is the phase constant phi naught. Okay, so everything else is the same amplitude, same angular frequency, same period, still a oscillation, a sinusoidal oscillation, but we have something different when t is equal to 0. So now let's ask for this graph, what happens when t equals 0? What is x at t equals 0? So x of 0 in this case is equal to a times cosine of omega times 0 plus phi naught equals a times cosine of phi naught. So now if you remember your cosine values, cosine will always be something between +1 and -1. So this value is going to be something, if phi naught is not equal to 0, it's going to be something less than 1. So our x of 0 is going to be less than the amplitude, and yep, that's what we see right here in our graph. So our phase constant phi naught allows for a different starting point. And this is also sometimes called a phase shift. So these graphs are the same, but they're just shifted. So this also accounts for that phase shift between the two graphs. Okay, so there's our phase constant. So that means our general equation for the position of an oscillator as a function of time is given by. So now we'll write down our general equation. So that the position of the oscillator x as a function of time t is equal to some maximum value of the amplitude times the sinusoid cosine times the angular frequency times time plus the phase constant. And then our special case, if it starts at the amplitude, our phase constant is going to be equal to 0. So there's our general equation of motion for that oscillator. The next thing we'll go on to is finding the velocity and the acceleration. What do those graphs look like, and what interesting things can we find out there?